Hey, welcome back, APers. We're going to finish up hearing and auditory transduction here in a video. Should be a little shorter, but we ended off last time right about here, and we're trying to talk about some theories about sound and how we hear different pitches of sound. We spoke about the basilar membrane in the previous video. Well, the basilar membrane becomes stiffer as we move to the top of the cochlea. And if we look at our diagram here, and we kind of spread out the cochlea a little bit, and remember we have the ascending chamber where fluid travels up here, and the descending chamber where the wave travels back out to the round window. And in the middle, right in here, we have the cochlear duct where the basilar membrane and the organ of Corti is, and all those tiny little hair cells. The stiffness of the basilar membrane allows different parts of the cochlea to correspond to different frequencies. Now, high-pitched frequencies tend to correspond to the base of the cochlea. And that means right down here in this area here, the beginning of the cochlea, if you will, closer to the stirrup. And if we rolled out, so if we look over here, if we rolled out the cochlea into a shorter little diagram, and the basilar membrane here is rolled out from the base to the apex. Higher frequency sounds from about 1500 to 20,000 megahertz are more active and detected at the base of the cochlea. So that it seems like the base of the cochlea responds to higher pitch frequencies where they peak. Medium pitch frequencies here from about 600 to about 1500 hertz. The wavelength kind of peaks in the middle of the cochlea. So kind of in this range here, that if we rolled it out, the wavelengths would kind of peak in the middle. And low pitch frequencies, as they travel towards the apex, from about 200 hertz to about 600 hertz, peak at the apex. So those kind of peak right in here. So it seems like different places where the wave peaks, high pitch down at the base, low pitch at the apex, kind of helps us determine the frequency of sounds. Okay, the frequency of sounds. And after those hair cells get bent, remember in the basilar membrane, those tiny little cilia on top of the hair cells bend and transduction takes place. That message, whatever pitch and amplitude that is, the auditory nerve travels to the thalamus, which is the relay center of the brain, and then to corresponding temporal areas in the temporal lobe, kind of in from our ears. And every place on that basilar membrane has a corresponding place in the auditory detection area of the temporal lobes. Now, there's a couple other things about sound that we need to know, like threshold. Remember we spoke about absolute threshold and signal detection theory and all that stuff. We measure sound in decibels. What is our threshold is conveniently kind of determined as 0 decibels. Now, we probably know we don't have an absolute threshold, but every 10 decibels we go up from 0 decibels to 10, 10 to 20, 20 to 30 decibels corresponds with a tenfold increase in sound intensity or loudness. So sound intensity is kind of the same as loudness. And a normal conversation, as you're talking in a room there's not a lot of people, you're talking to a friend in a quiet room, is about 60 decibels, okay? Now a whisper is only about 20 decibels. So if we go from 20 decibels, dB, to 60 decibels, we go from 20 to 30 to 40 to 50 to 60 decibels. So from a whisper, which is right here, to 30 decibels is 10 times greater. 40 decibels is then 100 times greater than a whisper. 50 decibels is 1,000 times greater than a whisper, and a normal conversation is 10,000 times more decibels than a soft whisper. And I'm not going to soft whisper right now because my microphone would pick that up. So the interesting thing is a rock concert. You go to a loud concert and you feel music, literally, is about 110 decibels. Okay? A normal conversation is at 60. So how many times greater in sound intensity is a rock concert than a normal conversation? I'll give you about 15 seconds. You can kind of go over with the neighbor. Okay. The correct answer there is about 100,000 times greater than a normal conversation. So you can imagine how sensitive your hearing is. It can hear a whisper, you can hear a normal conversation, and then it can also hear a rock concert. And what does that rock concert do to those hair cells, those little cilia cells? And we wonder how we lose our hearing as we get older, especially when you plug in those little earphones, those earbuds for your iPod, and you get that noise. It's probably about 100, 110 decibels when it's turned up. Now, we have about 100,000 hair cells in each cochlea when we're born, and those tiny little cilia, as we review, register when they move just a fraction of a millimeter, or the equivalency of one atom. So we have really sensitive hearing. It's kind of compared to moving the Eiffel Tower a half an inch to the left. We can detect that sound. So damage to those hair cells is like putting really heavy furniture on carpet fibers. Fibers they may never bounce back. Which might lead to a ringing in the ears, which you might have after leaving a loud concert. That ringing in the ears is called tinnitus. And that's, instead of those hair cells kind of standing up like this, after a rock concert, those hair cells kind of may be bent over like this and stay bent over, which means they're sending signals to the brain that they're bent and that there should be sound, even though there isn't any. Now, a soft conversation might be like walking on those carpet fibers and they bounce back right away, but loud noise is not so good. And remember, we're born with all the hair cells we'll ever have. Okay, about 30,000, 32,000, somewhere in that range. Nerve deafness is caused by damage to those hair cells, those ciliary cilia cells on the auditory nerve. And there are some noises that, like a close-range gunfire, can kill all the hair cells in your cochlea, rendering you instantly deaf. Not uncommon in warfare, early warfare. Or it could be just consistent exposure to very loud, high decibel sounds over time can also cause damage. Conduction deafness is caused by damage to the little structures that magnify sound. So damage to the middle ear, the ossicles, the eardrum, that can cause conduction deafness. And some other interesting things. Why do we not like to hear our own recorded voice? Well, when we hear other people's voices, we're hearing airwaves alone. But when we hear our own voice, we're also hearing bone conduction. So vibrations through our skull cause minor vibrations in our cochlea, as well as the airwaves that are amplified by the ossicles. And remember, loudness determined by the number of hair cells activated and how far they're pushed down. Soft sounds activate fewer hair cells. And a person can lose sensitivity to soft sounds and not loud sounds. So we hear the loud stuff, but we don't hear the real soft stuff. So we hope our teachers do when we get older, right? Teachers get older, they don't hear the whispers, but they still hear the loud sounds. Don't worry, I can still hear those soft ones. Now, pitch perception, and we've spoken about this really. There's a couple different theories, just like there's a couple different theories for color vision. Place theory says we hear pitch as associated to the place on the basilar membrane where those hairs are stimulated, and we spoke about that. That kind of best explains high-pitched tones. And the frequency theory deals with the wavelength frequency, is the rate of nerve impulses that those hair cells bend and they travels up the auditory nerve at the same frequency, kind of matches the frequency of the tone we're hearing. And this is best for just describing low-pitched tones. One other factor here is the Volley principle. When we add that to the frequency principle, helps explain higher frequencies than we can hear. Since frequencies travel, they travel greater than 1,000 cycles per second. Since our nerve cells can only fire 1,000 times per second. What that says is that some of our hair cells, they're lined up in different places. When these are firing at its maximum rate, and then they reach that refractory period, then these will wait to send their signal, and then when these hair cells can't fire, these hair cells will fire. And now we get back to the original hair cells. They're capable of firing now because they regenerate. So after that third row can't fire, then these will fire and so on. It's kind of like old school military firing when one row of soldiers would fire and then they kneel down to, as they kneel down to fire, the next line will fire and so on. So they'll fire in a volley with constant firing going on. And as we wrap up here, another interesting component that we do want to mention is echolocation. That's the ability to detect the location of a sound due to differing intensities and timing of the sound hitting each ear. Now remember, we have ears on opposite sides of our head, and sound travels at about 750 miles per hour, which means that if we're looking straight ahead and a sound comes from our right side, that means there'll be a different timing between those signals being sent to our brain and each ear detecting the sound. And it could be as little as 2,700 thousandths of a second from sound reaching our right ear to our left ear. And we can detect that difference, and then we'll turn our head to the right. So basically that means that we can detect that sound going, I don't know what that means. I don't even remember why I had that in there. 670,000 miles per hour, which I believe that's the speed of light. 670 million miles per hour. So we're just going to ignore that. But we can detect just a subtle change, a subtle difference in timing from one side to the other and detect that location. Other animals like bats will send out high-pitched frequencies and be able to navigate through a room in total darkness because of that. So we're going to wrap up. That's about it with hearing. We'll ask some questions when we get back to class, and I hope this helps out. Good luck.